Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Farhad Ali, your instructor for the subject viscous fluid. I hope this lecture will find you in very good health. This is the fifth online lecture, and maybe this will be the last lecture of this course. So far we have studied the pre-midterm. In the pre-midterm classes, uh, we had discussed in detail the Laplace transform and how to solve some problem by using the Laplace transform to find the exact solutions of the flow problems. And then after the midterm, post-midterm classes, in the post-midterm classes, uh, we discussed some flows in channels and in vertical plate, okay, in a rotating frame. Still, there are some we have some investigations, flow investigations, but as it is the last week of this course, so maybe we will discuss this uh, later, or even you can study it by using the same procedure, the same methodology. You can solve the flow problem, the model, by Laplace transform or some other assumed solutions. But the exact solutions, if you want to obtain the exact solution, so we apply the Laplace transform technique. But you know that always uh, uh, the inverse Laplace transform is not possible because it has some difficulty. So for this we have to move some numerical solutions, numerical Laplace transform, or we have to adopt some other assumed method. Okay, so we have studied in the previous lecture. We investigate uh, we investigated the flow in a rotating system. The fluid, we have considered the fluid, Newtonian viscous fluid, and uh, we solved the problem by using the Laplace transform technique. And we not only we didn't use only the direct formulae, but we have derived that formulae for the Laplace inverse. And by long process of inversion formula, we have used the inversion formula and we obtained the Laplace inverse. And in the assignment, I have given you the same problem by using some other method, which is called assumed periodic solution. Okay, so when you see, if you can investigate, if you investigate by using the assumed method, you will see that for the resonant case, when the force frequency becomes equal to 2 times of the natural frequency, okay, when they become this relations, when omega equal to 2 omega, small omega is equal to 2 uh, large omega, okay, so then you will see uh, that in that case, you will see that the a condition at infinity will not be satisfied. So this is one of the drawbacks of the assumed solution, of the assumed periodic solution, that resonant case, the mm, away from the plate, the bondolier does not control, and its amplitude is increasing and increasing, uh, which will um, make the destruction or collapse of the system. So that's why that sometime you will see that uh, for the infinity case, when the away from the plate, we call this the boundary condition, the second boundary conditions, we have no physical solution. But you can see in our problem, while investigating by the Laplace inverse, that both in both cases, for infinity also we have some physical solution. Physical solution means that at infinity it should be it should be come to rest at equilibrium point. If it doesn't come to the equilibrium point, so it will be not physical solution. So this is the continuation of the previous lectures, but with little bit extension. We have investigated. We investigate. Okay, the previous problem by adding some more terms. Okay, so this will be different. You will see. You can compare these model with the previous model, and there will be a little bit one parameter addition, and that one parameter additions makes the calculi quite complex. You will see this one. Okay, so now if you look at the title, the title is unsteady flow of Newtonian viscous fluid past a porous oscillating plate. So this is very important. Look at this one in the title: porous oscillating plate in a rotating frame or in a rotating system. So all the things are same. Unsteady because the study depends on time. Okay, the flow depends on time, so we call this unsteady. The fluid is Newtonian viscous fluid, rotating system. Already we have studied this in oscillating plate. Already we non-torsional oscillation we have studied in the previous lecture. But look at this one. This thing is new now. Now the plate is not rigid. The plate is porous now. So what is mean by the porous plate? Okay, so the porous plate means that uh, the fluid which is passing through the surface, that surface is not rigid now. What does mean by rigid? Okay, so that means that the flow come across, okay, the plate, means the plate is now porous, not rigid. And if the water level of the underground water is high as compared to the mainstream flow, if the flow is moving in the river, okay, for example, and underground water table is higher than, okay, is high, so then from the water from the deep from the ground, uh, okay, will cross the plate and will join the mainstream. And if the water level is very low, underground water level is very low, so what will happen, the flow will uh, uh, cross the plate, and it will move downward. Okay, so there will be, we call this suction. Okay, the ground will suck the fluid, and if the water level is higher than the mainstream, the water um, from the ground will blow, okay, or will inject into the mainstream. So this is called porous plate, or this is called suction and injection. We call this suction and injection. Okay, So material, I will upload material on suction and injection. So please you read to those materials, and it will make clear your concept about the suction and injection. It is very important. Okay, there are many significances of the suction and injection. Okay, if you know the scarp. Okay, the scarp, we many areas having the water table high. Okay, those area we having uh, high water table. Okay, sometimes we call this mm, that is seam and tor. Okay, so when the water table high, so what happens, it is not appropriate for the are good for the agriculture purposes, because of there's always water. Okay, in the soil, and it is not good for the cropping or growing crops. Okay, to grow something in the soil. Okay, so how the government or some uh, institute. Okay, from the agriculture sector, they dig. Okay, and put the porous pipes in the ground, and that small porous pipe in the ground. Okay, the pipes, the normal pipes which we use for the sanitation, but they are porous. They just make pores um, in that pipes. Okay, and then it kept in the ground. Okay, uh, and then it is connected. This is the network of small porous pipes, and then these porous pipes are connected with the big pipes. Okay, so the water, it sucks the water. It sucks. Sorry, it inject the water blowing um, from the you can say that the pipe sucks the water, or the waters blow from the ground to the pipes. Okay, inject from the ground, and the pipe sucks this water. And there are these are the many this is the network of the porous pipes. So it sucks the water from the ground, and it transfer to the main pipe, and the main pipe is connected with some canal or some river. Okay, so the waters comes out from the soil to the mainstream. Okay, and in this way the water table of the ground decreased. Okay, and after some time you will see that the waters the soil becomes dry. Okay, and then by using these methods the soil becomes suitable for for growing the crops. Okay, so this is very important, and there are many physical significance. So I have many literature on this. You can see literature, and I will upload this because I don't have time uh, to discuss this in detail, because we have to investigate the problem. But this is the theory. Okay, especially in the seepage flow, when there is seepage. Okay, so this is all about in the about a porous plate, or due to the suction and injection. Okay, and in hydrology, seepage flow refers to the flow of a fluid means water in a permeable soil layers such as sand. The fluid fills the pores in the unsaturated bottom layer and moves into the deeper layers as a result of the effect of gravity. The soil has to be permeable so that the seepage water is not stored. Okay, so uh, similarly, if you talk about the groundwater, um, so this is all about. There are some literature about this. Uh, so we have to, okay, please you go through this literature, okay, because you can see this is all about the seepage and in suction and injection, okay. So if the water level is high, okay, so it will join this stream, and if it is the water table or the water level of the underground water is low, so this water will suck into the ground, okay. And because look at this one, when there is rain, so the fluid, this soil, this now look at, this is your plate, and this plate is now permeable. This is called porous plate. The water of rain will be sucked by this ground, okay, by this soil, and it will move to the deeper layers. So, and then when you are digging to use the water for drinking, you will dig, okay, you will dig the ground, and then you can inject the water from the ground, and this is called suction and injection, okay. So far we have considered that this surface is rigid, like the floor of our room. When you will allow the water on this, on our room floor, so it will not be sucked by the ground, or no water will inject from the ground, okay. The same water will be, so the ground or the plate which does not allow the water to pass uh, to to pass through it, okay, is called a rigid plate or rigid surface, okay. So you can see these are pores, and these pores are interconnected to each other, which are called permeability, okay. So in this way, um, uh, if the water, as I discussed earlier, if the water table is very high and the soil is not appropriate for for the agriculture purpose, so then we have to put porous pipes, the network of porous pipes, and it will the porous pipes will uh, suck the water from the ground, from the soil, and this will make the soil fit for the agriculture purposes. So I will upload these materials, so please you go through this thoroughly, and you will see that, okay, there are many, okay, interesting significances and applications of this porous or suction injection, okay. So porous plate means suction and injection, so we will investigate this one, okay. uh, uh, okay, so this is the one title of this, and this title may be like in this, the three-dimensional bondelier flow of Newtonian viscous fluid past a porous disc in a rotating frame. So we have said they're three-dimensional. For example, if the, because this is the 2D, um, in rotation, as the flow uh, is rotating, so what does it mean? That the flow is in, there is a real flow and imaginary flow, so it will be 2D. And also there is suction, so suction is in the x, the z direction, so all the velocity components u, v, w will be engaged or involved in this flow, okay. In u direction there is flow, in v direction there is flow, and in z direction, you see in z direction the flow is rotating also, and there is suction injection. So all the three components are engaged in this uh, mm, uh, in this flow model, okay. So we can say that this is a three-dimensional flow, okay. And the disk is porous, means there will be suction injection. The flow will move across the plate, okay. If the flow is moving across the plates, means the flow move far to the ground, or the flow comes from the ground. So this is called suction and injection. Uh, okay, and that is called porous plate. So let me start to model the problem for this kind of flow, and you will see that only one term will be extra as compared to the previous study investigation. There are some assumption which we this is actually, yeah, this is repetition, because we have already discussed these assumptions in the previous lecture, but there may be, okay, yeah, of course there is some uh, okay, there is some addition in the assumption as compared to the previous lecture. As you can see, we have incompressible Newtonian viscous fluid, but the second one was not in the previous lecture. That is, now the plate is porous, no rigid plate. Okay, so the plate is now porous, and same plate is oscillating. We impose this oscillation. This is not a natural oscillation. We impose the oscillation, and the fluid and the plate is experience a rigid body rotation. Okay, rigid body rotation, and I explained the rigid body rotation, okay, in the previous. So now the mathematical formulation of the problem, we consider the unsteady flow of Newtonian viscous fluid in a semi-infinite expanse bounded by an infinite porous plate. Okay, so the plate is now porous, okay, at z is equal to 0. So when there is z, that there will be plate. Okay, it means the plate is in the xy plane. Z is equal to 0 means the plate or the disk is in xy plane. Okay, just like your room. Okay, if you okay, imagine that you are sitting in your room. So the one wall is x, one is y, and the vertical wall, the vertical corner is just like z. So where there is z0, so the porous disk is bounded by uh, an infinite porous plate at z is equal to 0. And as the plate or the disk is porous and experiences uniform suction and injection, you can see from this figure. Okay, what does mean the arrow? If you look at the previous the previous lecture, there was no these arrows from, okay, from this side and from this side. Okay, so this one is means that okay, this is the water, the plate is porous, and from the ground the water moves. This is the mainstream. Look at this one. These arrows shows the mainstream. This is the mainstream. This is the mainstream. Okay, so uh, if this water from the ground moves and join this mainstream, this is called injection or blowing. And if the water table is lower, okay, the water table is low, so what will happen? The water from this mainstream will sip, okay, will move downward into the soil. Okay, the this is called the ground. This under this ground or this plate will suck the water from the mainstream, and this is called suction. So I hope now you will know that what is means suction and injection. Okay, so if the ground water, underground water table is high, so what will happen? The water will cross this plate, because there are pores in this plate, in this disc. So it will move and will join this mainstream. And if the groundwater table is lower, so what will happen? The mainstream, the water from the mainstream or the fluid from the mainstream will move downward to the deep layers. Okay, and okay, so if the waters uh, join the water. If the waters move from the ground and join the mainstream, that is called injection or blowing. And if the water from the streams moves downward, okay, and the grounds suck the water, okay, so this is called suction. So this is called suction, and this is called uh, injection. So we now, this is the innovation. Now this is the new thing we have added, okay. uh, and we will have some parameter for suction and injection. So there is also suction injection in the z direction, and the fluid is also the plates, and the fluid is also is experiencing the rigid body rotation, is experiencing the rigid body rotation, okay. So the other things are same, and just we have these things, suction and injection. We don't have these arrows in the previous disc, because that disc was not porous, that was rigid, okay, that was rigid. The previous plate not allow the water to go underground to move, okay, and then, okay, nor they allow the waters to join the mainstream, okay. So this was okay. That is called a rigid plate, and in a rigid plate, neither the water goes downward, nor the water comes from the ground. So we call this rigid disk. So now in this case, you see that uh, it depends, okay. Sometimes the water will move to the okay, to the ground, just like I gave the example. So this in the scarp, okay. So in the scarp, you see as I discussed, mentioned before, that they uh, uh, put, okay, in the deep layers, the network of small porous pipes, and then as I these are the scarp is carried out, is done in those areas where the water table is too high, okay. You will see the water on the surface, okay. So then when pipes are fixed in the deep layer, the porous pipes. So then, as the water table of the water of the soil is high as compared to the pipes, the porous pipe, so the water comes from the soil to the pipes, okay, and it joins the comparative larger pipes, and then the water is dig out to the mainstream, and this way the soil water table is gradually decreasing, and after some time it makes suitable for agriculture purposes. So this is all about of this geometry, okay. The disk is x and y plane. This is the disk, okay, and the fluid is above z is equal to 0. The fluid is above, when where the z is 0, so there is the fluid. So the z is 0 here and greater than 0. Z greater than 0, we have fluid. So the fluid is here, and also additionally this plate is oscillating. We have imposed oscillation on this plate at z is equal to 0, and you will see this will be reflected from the conditions, the boundary conditions. Both the fluid and the plate are in state of solid body rotation, okay. So with the constant angular velocity, this omega about zx normal to the plate. So the both the fluid and the plate are in state of rigid body rotation, with angular velocity uh, omega, which is omega, okay, omega about the z-axis, which is normal to the plate, okay. It is normal to the plate. Z-axis is the, this is the plate, and z-axis is normal to the plate, okay. So I hope this the geometry will be clear. You can you can describe physically the geometry now. You will be able to describe the geometry or to discuss the geometry physically. Additionally, a non-torsional oscillation of the frequency omega. So this will be the imposed or the forced frequency. Okay, this is the natural frequency and this is the imposed frequency. Omega will be the imposed frequency. So we already, this the plate is already imposed the additional non-torsional oscillation of the frequency W is superimposed on the plate in its own plane for t greater than 0. Okay, when the time greater than 0, so we have all imposed the this omega frequency. So now the constitutive equations for the flow are given as. These are some equations. The first one is the continuity equation. It must be satisfied. Otherwise, if it doesn't satisfy, no flow will be occur. Okay. So this is the continuity equation, and you know the, because this is in the three dimensional and this is the three directional flow. I have all the components of velocity u, v, w, and also all space variable. So three directional and three dimensional. Just I have written like this because our Newtonian equation will be in this form. Okay, generally they are in the form 2, equation 2 and 3. Okay, and there should be plus 2 omega u because the flow is rotating. Okay, you can see that this here is minus 2 omega v. We already discussed this and we have derived these things, and there should be plus. Okay, before this equal there will be plus this thing 2 omega u. Okay, so there should be mentioned this one. Okay, and on the left hand side the viscous forces, this is come from the dv by dt, and this is come from f m is equal to m. This is from ma, and this is ma is equal to f, second law of motion. These are forces, viscous forces. Now the velocity of the field for the given flow can be defined as, look at this one. The velocity is also, it depends on z only and t. It is unsteady flow and it depends on z axis. But all the components of u, the v is involved, u, v and w. Okay, so that's why we say that. Okay, using equation 4, look at here. The velocity field is u is only the function of zt. So when you use equation 4, that u is only the function of zt, v is only the function of zt, and w is the function of zt. So this equation 1 reduced because this is not the u is the function of z in t. So u is not the function of x, though the flow is in x direction, but this the flow is in x direction is constant. Similarly, the flow in y direction is constant. Uniform flow, developed flow. So that will be 0, that will be 0, and just we have partial w by partial z is equal to 0. So equation 1 reduces to, when we use this equation, equation 1 reduces to this thing. Partial w by partial z is equal to 0. To find w, we integrate both sides. Okay, just write like this, partial w or dw is equal to 0, and now integrate both sides. We will see that integration and integrate sign and d will be cancel each other. We will have w and some constant of integration, and that constant of integration, we say that, let's say the constant of integration is minus w naught. Okay, we have considered that this constant is minus w naught because this is constant and w naught is also constant, and if we put minus, so minus is also is constant. So where w naught is called, look at this one, this is new for you. Okay, so now we have calculated w. So w is not because the derivative of w with respect to z is 0. So what does it mean? That w is constant with respect to z. What does it show? If you take the derivative with respect to z and the result is 0, so what does it mean? That this w with respect to z is 0, or this is constant. So now w is constant, and we denote this constant by minus w naught. Where w naught is called suction and ejection parameter. Now look at this one. We have introduced these things. Now this thing is new. This thing is new now. This W naught is called the suction and injection parameter. Okay, so uh, and remember, when W naught is greater than 0, when this W naught is greater than 0, other than, okay, don't mention this negative sign. This is in bracket, let's say. So if W naught is greater than 0, for example, plus 2, the value of W naught, not with minus, okay, okay, W naught value. So when W naught is greater than 0, means positive value, we call this, it is suction, and it is called suction. And if W naught is less than 0, if W naught is less than 0, if the value of W naught is negative, then it shows injection, or it is called injection or blowing. Okay, look at this one, blowing. It will move from the ground and will join this main stream. Okay, blow, we also call this blowing, when something is blow from the ground. So this W naught is called suction and injection parameter. When it will be suction? When W naught value is positive. When you put W naught as a plus 2, so that will be suction. If the W naught value is minus 2, so then it will be injection. Now in the absence of pressure gradient and using equation 4 and 5, equation 2 and 3 take the form. Equation 1 is the velocity, equation 4 is the velocity field, in where we have shown that u is only the function of zt, and 5 is that w should be replaced by minus w naught. So the governing equation 2 and 3 takes the form. Okay, let's see, uh, partial u by partial t, how to reduce this equations. Look at this one, equation 2. Look at equation 2. Yeah, of course, u is the function of t, so we will have this will be left. Okay, u is not the function of x, 0. U is not the function of y, 0. And w is equal to minus w. Okay, w is equal to minus w naught. We replace this w is with minus w naught, as we have calculated this thing, partial u by partial z. We will have this minus 2 omega v minus, in the absence of pressure gradient, so this will be equal to 0. Mu, u is not the function of x, 0. U is not the function of y, 0. And only we will have this term, partial square u by partial z square, which will be multiplied with mu. And similarly, equation 3 will be simplified or reduced to, so look at this form. Equation 2 and 3 takes the form as shown in equation 6 and 7. So now you can see w is replaced by minus w naught, also minus, there is also w, so it has been replaced by minus w naught, and other things are same. And from the right hand side we have only this term, because the other terms tends to 0, because u is not the function of x and y, and v is not also not the function of x and y, and the pressure gradient is absent. Okay, the flow is not due to the pressure gradient. There is no role of pressure gradient in our model. Okay, with the following physical conditions, look at, when at z is equal to 0, means on the disk will experience this kind of oscillation. Okay, this is called the torsion, the non-torsional oscillation. So this is same like the condition as in the we have described in the previous lecture. We have shown in the previous lecture. Okay, we have taken in the previous lecture. But look at this, only this thing is now, because we have added this thing, that and also you will see that what is u and u1, that is constant. The u is constant, u1 is constant, and having the dimension of velocity, so that means it shows like constant velocity and constant velocity. Okay, so as there is some suction and also some injection, so also we have some negative sign with this one. Okay, Okay, so that means uh, maybe velocity may be decreased or increased. Okay, at the role of suction. Okay, if the flow moves from the ground to the mainstream, so what will happen? The stream flow will increase or decrease. Similarly, if it is from the mainstream, if the waters of the fluids comes or moves down ground, okay, to the deep layers, so also it will affect the flow of the stream, and the stream flow will increase or decrease. So at z is equal to 0 means on the disk is also oscillating with this, okay, and you know what is a and b, these are a complex constant, okay. So this is the conditions which we have imposed on the boundary or on the disk and away from the plate. Similarly, but for the plate which is in the on the axis, along the x-axis, it has oscillating, but the portion which is not at the y, okay, so that should be 0, or we can take as like as we have shown before the same thing, but v, okay, u plus iota v complex velocity, and it is also become now because this is a complex velocity, so there may be the role of the v, uh, the plate which lies on the v axis, it is at rest, okay, and has zero rest at z is equal to 0, and it away from the disk, away from the disk away from the disk means, look at the geometry. Look at this geometry. This is disk. Away from the disk means, look at this, if you move away from the disk, okay, away from the disk, maybe somewhere here, this oscillation will, this disturbance, or this torsion oscillation which we have imposed on the disk will not affect the fluid here, and the fluid velocity will be 0, okay. So this is away from the plate, and this has been shown from the second boundary condition, okay, from this one, that away from the plate when z tends to infinity, away from the disk, both components of velocity will be 0, u0 and v0, okay. Where u and u1 are constant with the dimensions of velocity, and a and b are complex constants, okay. uh, Equation 6 to 8, and you know this is quite, you are quite familiar with this one, because you know this is actually nothing but these are the primary and secondary velocity, and we can join this as a complex velocity, and we have already done this, or the calculi behind this has been, the calculi behind this have been provided in the previous lecture. So equation 6 to 8 can be written in more suitable form. 6 and 7 give us this, and 8 gives this, okay. So this is now in this form, in the f form, where f is u plus iota v, where f is equal to u plus iota v, the complex velocity, okay. So now f is the complex velocity. It is the sum of real velocity or imaginary velocity, or it is the sum of the primary velocity and secondary velocity, okay. So now we have two boundary condition, f of z, when on the z we have this velocity, and beyond the z, away from the z, we have zero velocity. Now for the solution of equation 9, we will solve, of course, now we have model, okay. Now we have this model, we have PD, and we have also the given condition, so we can solve this one, and we can then if show the effect of various parameters on this flow, then you can say that uh, what will happen if we increase the suction parameter or injection parameter. The flow will be increase or decrease. And also I have some example okay. Also we have sketched some graph by suction injection. So if I found, so I will also discuss those figures schematic, okay, those sketched. So now we will our objective is to solve this differential equation. To how solve this differential equation? If you want to use the periodic solution, assume periodic solution, or you want to apply the Laplace transform technique or in our Fourier technique, okay. So are some others method or separation of variables method. So this is up to you. So how to solve this equation 9? What I'm doing, I use the Laplace transform technique to find the solution. Okay, and you are quite familiar how to, because I have solved the previous problem by using Laplace transform, and we will adopt the same procedure, maybe a little bit different, but the same procedure. Okay, that how to find. We know that if we have function of t, if you have a function of t, so the Laplace of that function will be like this. F bar zs, t will be changed to s, okay. And by definition of Laplace, that will be equal to 0 to infinity. How we get this? We get this from this integral, from this e power minus st f of t dt, okay. So if you put this f of t here, so the result will be f bar z of s after calculating this integral. So this, we will use this definition to solve equation 9. Using equation 11, equation 9 transforms to, and you know how to get this one, okay. So you know that partial f by partial t will be s, okay. F bar z is this one. So you know this, how to apply on this on time. So it will give you s f bar zs minus f of z 0. Initial condition is 0, and this will just change to df bar by dz, and f will be just change to f bar and d square f bar by dz square. So you can try this one, okay. I just skip one or two step, you okay, which I already provided in the previous lecture. So this is a quite lengthy lecture, so that's why I will try to skip some steps, so you can derive this thing. You can do like this. How to get from 9 this equation 12? So, and also with the transform boundary conditions. So the boundary conditions are also transformed. Minus u, the Laplace of constant is u by s, okay, and the Laplace of exponential function e power iota omega t is s minus iota w, and e power minus iota omega t is s plus iota w. Is greater than 0 and z greater than 0. And this is the second boundary condition, that at infinity, both the plane, in both plane, at z, when z is to infinity, in t plane also the complex velocity be 0 away from the plate, and in s plane also the complex velocity is 0. Now the auxiliary equation for equation 12. Now, as you know, now the PDE, this is the beauty of Laplace, that the PDE has been changed to ODE. Now this is ODE, only one independent variable, okay. Look at this one, only z independent variable. So the PDE has been changed to OD, and this is the quadratic equation, and the auxiliary equation for equation 12 is m square plus w naught nu m minus 2 iota, minus I have taken m minus common, 2 iota omega plus is by nu. Okay, so how to find m? This is the quadratic equation, and we have these two roots, minus b plus and minus b minus. Putting the values, we have m is equal to this thing, okay. Now the general solution will be, these are the two distinct roots, two distinct real roots, okay, are two distinct roots, because this is distinct, there is no iota, okay. So this is will be considered as real roots, and they are distinct. So E1 positive root minus 1 plus this thing, and C2 e power minus z negative root. So when we take minus common, so that will become minus and that will become plus. Okay, so now this is the general solution of the equation 9. Now we have to find the values of constants C1 and C2. How to find the values of C1 and C2? We will use the boundary conditions. Let me use the second boundary condition, the condition at infinity away from the plate. So we already said that the complex velocity is 0 away from the plate, and we put z tends to infinity because this is z. So put z tends to infinity, we have c1 e power infinity. So what does it mean? C1 of infinity is 0, so e power infinity is not equal to 0. So that means C1 equal to 0. So now when we put C1 equal to 0 in equation 14, C1 0, so this will be managed, and just we will have this one. So now look at equation 15. In equation 15 still we have C2 the constant. We have to remove this to find the value of C2. So we will use the first boundary condition that at z is equal to 0. When we put z is equal to 0, so just we have C2 f of 0s. F bar of 0s is equal to C2, and you can see what is the value of f bar 0s. What is the value of f bar 0s? Look at here. In a transform boundary condition, f bar 0s, z is 0, it's quite clear. The value is this thing. So put this value in the left hand side. That will give you the C2 value. So now the C2 value is this thing, minus u by s. So put C2 values. When you put the C2 values, this is the C2 values, okay, and look at this one, C2 e power, this is C2 value, and we have this thing, e power, this is the root, the negative root. Okay, so now equation 16 can be written in more simpler form. Okay, individually we multiply, we open this bracket, multiply this, this multiply this, and this multiply this. So in more appropriate form, equation 16 can be written as. Okay, and also to take now, once we apply the Laplace transform, now we have to find, because our our PDE is in ZT, not in ZS. So now we have to change this S, and this is only possible to take the Laplace inverse of this thing, left hand side, and Laplace inverse of the right hand side. So when we take the Laplace inverse of the left hand side, look at this one, taking Laplace inverse definition, that Laplace inverse of f bar zs, which will transform to t, s will be transformed to t, is equal to fzt. Look at this one. When you take Laplace inverse of f bar zs, so this will be cancelled and s will be changed to t. And definition is 1 by 2 pi gamma plus minus iota infinity are only gamma to gamma. Okay, this is only gamma contour. This is the contour. Okay, and that is gamma minus infinity, gamma plus infinity. Okay, are 0 to infinity. Okay, using equation 18, the Laplace inverse of equation 17 is, look at this one, we just put here the Laplace inverse of the left hand side is zt, but now to find, this is the Laplace inverse, but now we have to find the integral. Okay, so you can see this is just I put the values, nothing else. Okay, the definition. Okay, this is f of s, and this is f of st ds. Look at in the definition, e power st f of s ds. So f of s is this thing. Okay, we have, this is f of s, this is f of s, and this is f of s. So we because there is plus operation, plus minus, so we will have three integral, e power st f of s ds, f of s ds. Okay, so now our main goal will be to find these integrals, to find these integral. Okay, now this our objective will be to solve these integrals. Okay, and that will be the solution. This is also a solution, but still, if you look at here, there is s. Okay, so we have to shift this s. You will see in the answer, the final answer, there will be no s. So now we have to solve these integrals. So we will use some techniques, and look at this one. This is more suitable form. I just uh, taken out the constants. Okay, and look at equation 20. In equation 20, because in every integral we have this common. Okay, w by 2 nu. So just keep out this e power minus zw uh, 2 nu. Okay, we have minus u I1 plus u1a I2. Look at this one, u1a, and 2 pi, this thing is I2, and u1b I3. So this thing divided by 2 pi iota, this will be I3. So we are, let me take one, because if I show this, I1 is this, I2 is this, I3 is this, so it will take, okay, and just will waste time. So just I have, because I just starting to solve one integral. Okay, so okay, let me take, you can take this as I star. Okay, not I1, but you can take this I steric. So when we solve this I steric, okay, and we get the solution, we solve this integral. So we will just incorporate, look at this one, when we solve this integral, so how to find the others. Okay, if you solve this generally for I steric, I have put this I1, but if you put here, this is I steric, not I1, or just I. Okay, I think it should look at you put just I and solve this one. When you solve this one for I1, we will replace, uh, you can see the difference. Okay, at the end you will see there is no iota omega, so means omega is 0. So when we find uh, uh, the value for the I, so when we put omega equal to 0, that will give us I1, and when we put omega as omega, okay, we will replace omega by omega, the same thing, that will give us the value for I2. And when we finally replace omega by minus omega, so that will be the result for the I3. Okay, so I just taken I1, but you can take like I, and then you can replace omega equal to 0, omega equal to omega, and omega equal to minus omega. That will give you I1, I2, I3. But I have taken this I1. So let me start to solve this one. Okay. So look at uh, we first solve I2. Okay. Okay. Just I told you that you can take this I steric, not I2. Just take I steric. Okay. And I2 is like this one. This is I2, 1 by 2 pi iota. This is I1 and I2. Okay, this is I2. This thing, this integral divided by 2 pi iota. This is I2. Okay, so when we solve I2, we will replace omega equal to 0. That will be I1. That will give you I1. And when omega is replaced by minus omega, that will be calculus for the I3. So quite simple. Just we need only one to solve. Okay, so look at this. This is I2. Okay, we take this thing without s. Okay, what I did in this one, you can see I just common new here. Okay, because I want to keep s, okay, isolated. So I I'm going to take this new common. So this new, when comes out from the integral, so it will be under root new. Okay, so look at this one. When I take common new, so this will be new and this will be 1. Okay, so look at this. Now you can see s is now have been isolated. So now I just represent this for simplicity, because it's the two terms, so it will make easy to represent this by one because this is constant, and we can represent this by another constant, the sum of these two constant by another constant. We can do this. Okay, don't join this one, because this is the variable. There should be, sorry, there should be ds. Okay, there is ds. I have, okay, miss or didn't write ds, but there is that is differentiating with respect to right here ds. So with respect to ds, s is variable, so you cannot let lambda plus s. Okay, so you can just for simplicity, uh, you can do that. The sum of, you can represent the sum of many constant by only one constant. So this is another constant. So now look at this one, it make easy, and look at this one, it's quite simple now. I replace lambda by this and plus is ds. Okay, so now our objective will be to solve the integral. Okay, now I introduce uh, another new variable, dummy variable, that is lambda square is equal to eta square is equal to lambda s. The radicand of this integral is equal to eta square. Eta square is variable. So differentiate both sides. 2 eta d eta, lambda is constant, so the derivative of eta is 0 and ds. And also this implies that eta is equal to, sorry, lambda is equal to eta square minus s, or lambda is equal to, and s is equal to lambda square minus eta, because we need to replace the values. So eta square is equal to lambda s, and s is equal to lambda square minus eta. Okay, differentiate these two. Now replace the values. On ds we will replace 2 eta d eta e power z by mu. Look at this one, z by mu, and we have lambda plus s. So lambda plus s is equal to lambda square, and the square root of lambda square is eta. Okay, so now just we have z by mu eta, plus we have st, there is plus st, so the s value is given here, lambda square minus eta, lambda square minus eta into t, and in the denominator we have s minus iota omega. So we have the s value, s is lambda square minus eta and minus iota w. Just replace these value in the above equation, and after simplification, okay, 2 will be cancelled with the 2, this 2 will be cancelled with this 2, and look at here, this e power, sorry, this e power lambda t, take it out because it is constant with respect to d eta. Lambda t e power minus lambda t is a constant with respect to eta. So this is constant, so keep it out. So now we have this thing. This is the simple form. Now again we introduce, because lambda is constant, omega is constant, so we can represent this by another constant to simplify. Now we can show the two term by one term. So it is okay. So it will make the system simple. So now we become lambda square minus c, lambda square minus c, because we just changed lambda plus iota w by c. And again we now introduce another variable, demi variable, that is xi. That we say that lambda square minus c, the denominator is equal to another uh, demi variable xi, and eta is equal to, or eta square is equal to xi plus c, or eta is equal to xi plus c under the root, and xi square will be xi plus c. Now differentiate this. So 2 eta d eta, and c is constant 0, and d xi. So eta d eta, shift this 2 to the right hand side. So you have eta d eta value. So this is your eta d eta value. So replace this d eta, eta d eta value by 1 by 2 xi, lambda square minus c is xi, and also we have eta value which is equal to xi plus c, and the eta square value is xi plus c. Okay, so look at after substitution, or after substituting the value, or after substitution, we have I2 like this, or you can, I already told you, you can see this by taking by as I steric, or simple I, capital I. So now we have this thing, and again if you look at Ct, which is constant with respect to xi, so keep it out, plus Ct, and just we have this thing. Okay, so now we have a built-in formula which is already published in literature. So we have this formula. If we have 1 by 2 pi gamma, okay, the limit is same as in the formula of Laplace inverse, because you can see that they are look at first let me the first demi variable. So there will be no change in limits, because look at the s is variable and eta is variable, so they are positive related with each other. So if s is 0, so lambda will be 0. If s is infinity, so lambda will be also infinity. So they are not inversely related, so there will be no change of limits. Okay, similarly in the second substitution, also look at the relation between eta square and xi. They are positively related. When xi is 0, so eta will be 0. When xi infinity, eta will be infinity. So that's why there will be no change of, because um, one scholar has asked about the limits in the previous lecture, that what will be the effect of limits on the while you are using the substitution. So I have cleared it, but now okay, for the whole class, okay, if they have confusion on this, that what will be the limits, so what will the limits will be, there will be no change of limits when you uh, because now we're changing the one variable with another variable, but they have positive relation, and there will be no change in limits. Okay, and so we have this formula that we have 1 by 2 pi I, okay, gamma minus infinity, gamma plus infinity are 0 to infinity, okay, because our domain is from 0 to infinity, no minus infinity involved. So we have, if we have this formula, if we have, look at this integral 1 by 2 pi iota, and we have z xi plus c. So this is the variable and this is the variable, and plus xi t, xi with t, and also we have in the denominator xi. Okay, so for this we have this formula. For example, if we have e power zt minus b, I just written this z xi t as first. e power zt minus b z plus a square. So these two are okay divided by z. So we have a product of z with t, product of this variable due to which it is differentiating. We have dz, so zt. Also we have in the radical z plus a square constant and divided by this variable z. So for this we use this formula. Look at this formula: 1 by 2 e power ab er of c b by 2 under root t plus a under root t e power minus ab er of c b by 2a minus at. There is plus, there is minus, there is plus, there is minus. Okay, so now uh, use this formula for this one. Okay, both are same, so we can use here a b. You can see in the a we have c, a square, on a square we have c, so a square is equal to c, and on z we have b. Okay, so a square is equal to c, so a will be equal to under root c. Where there is a we will replace by under root c, and where there is b we will replace this by z under root nu. Okay, now in this case you can see where there is b यहाँ पर, okay, where there is b, sorry for the transition, where there is b we have this thing minus b, so this is minus this thing, so this is z by nu, so b is z by nu, so replace a by under root c and b by z under root v. So I2 becomes e power minus lambda t ct divided by 2. This is the formula 2 from the formula z under root c by nu er of c z by b by 2t. So b is z by under root nu and 2 under root t ct and minus ct and minus. That's just only the difference of. Now again we have to transform it to the original variables to replace the constant into original constant and the dummy variables to original variables. So first we try to replace lambda by c minus iota w, where c is equal to this thing. So put here c, the c values. So lambda is equal to this thing. So lambda is this thing and c is this thing. So replace c by this and lambda by this. In the above equation, we get these things. Okay. So now this is c under root c, this is ct. So this is the c value. Okay. And in the above equation, there is no lambda. Yeah, we have c minus lambda t. Okay. So lambda is outside of the, yes. Lambda t, and this is ct. This is the lambda value, this is the c value. And look at t is constant, also t is t, so we can take t common, okay, from both. And let's see what will happen. Okay, if take t common, so it will cancel some terms, and you can see we can get I2 in very simple form. E power iota omega t, this thing. Okay. Now, yeah, if this is I steric or if this is I2, so what will be I1? I1 will be, if we put this omega, where there is omega, put this omega equal to 0. Omega 0, omega 0, omega 0, omega 0. Okay, so this will give you I1. And for I3, replace this omega by minus omega. This should be minus omega t, minus iota omega, minus iota omega, minus iota omega, and minus iota omega. So no need to follow the same procedure, the long procedure which I have done for this I2. So you just replace iota with minus iota for I3 and iota equal to w equal to 0 here, For I3 only W, because I will get W for minus W, and W equal to 0 for I1. Okay, if one, we have already derived the formula by using the formula. Okay, or put omega equal to 0, not iota omega, just omega equal to 0, because the result will be same. Omega equal to 0 in I2, that is I1 is equal to this thing. Okay, put in I2 omega equal to 0, you will get this thing. For I3, yeah, I think for I3 we have already calculated. This is for I3. So we have replaced uh, for I3, just change iota with, omega with minus omega. So which is already changed. I already changed this. Okay. So now you have I1, I2, and I3 value. Substitute in equation 20. Look at equation 20 if you have. Recall your memory. What is equation 20? Yeah, this is equation 20. We have now I1 value, I2 value, and I3 value. So put in this one. Okay. So we have just you have to substitute, replace I1, I2, and I3 by by their values. So we have, okay, this thing. This is the this solution describe a general solution of the unsteady Bondelier flow in a rotating fluid, including the effect of uniform suction and ejection. W naught is uniform suction and ejection. Okay, this is the unsteady flow. So this is your answer. And if you want to satisfy the condition, so this is your homework to find that for z is equal to 0, for z is equal to 0, we have um, f of 0t equal to minus u plus u1a e power iota omega t, and plus u1b e power minus iota omega t. Okay, when z is equal to 0. So look at here, when z is equal to 0, you will have minus u only by 2. You will have only ERFC of this thing and ERFC of minus this thing. So ERFC of this thing will be 2 times this thing, and okay, 1 plus this thing and 1 minus this thing. So it will be cancelled, and you will see 2, only 2. The result will be 2 from this bracket, and 2 will be cancelled with this 2. So just you will have minus u. Same do for this thing. Okay. So and for z is equal to infinity, the result is far away from the plate, the velocity should be 0. So of course, this is e power minus infinity, and e power minus infinity equal to 0. So this will be equal to 0. E power minus infinity equal to 0. This will be 0. E power minus infinity 0. Okay. So you can verify, and also I partially verified that the above equation, the above general solutions satisfy both the conditions. Okay. Now, as I have told you, as we had discussed in earlier classes, that when we have unsteady flow, so that flow is actually the sum of steady and the transient solution. So also in the above equation, that is equation number 20, we have a steady state solution. So how to reduce the equation 20 into steady state solution, that we have to put t tends to infinity. Already you have tried this. Okay, so you know this. I have done two things together, that I have put t tends to infinity in the above equation, and at the same time I have taken the resonant case where your force frequency becomes equal to the 2 times natural frequency. So this is called resonant case. So I have taken the resonant case that you can okay, in the literature you can see that many solution at the resonant case does not satisfy the condition at infinity. Okay, so now you can see that if we consider the resonant case, that is where force frequency is equal to 2 times natural frequency, this situation is called resonant. Okay, so at the same time I put t tends to infinity, and also omega is equal to 2 omega, small omega to the big omega, 2 times small omega. Okay, so if there is omega, small omega, omega, that's just like w, it will be changed like this one. So this will be changed to 2 omega. So 2 iota omega plus 2 iota omega will be 4 iota omega. And in the third, in the I3, they will cancel each other. 2 iota omega minus 2 iota omega, that will cancel each other. So the result will be, and also I will put t tends to infinity, ERFC infinity, ERFC plus infinity, ERFC minus infinity. Because when we put here t infinity, that will become 0. And here t infinity, so that will give you infinity. So ERFC plus infinity and ERFC minus infinity. As in the previous lectures, we had discussed this. Okay, I have done this. In the I1, there is no omega, so that's why we have this thing. Okay, but in the second, we have iota omega has been replaced by 2 ohm, so we add, is become 4 iota ohm, omega, 4 iota omega. And in the third case we have iota 2 iota omega minus iota omega, so that becomes okay, cancel each other. And we have ERFC plus infinity, ERFC minus infinity. And you know that ERFC plus infinity is equal to 0, and ERFC minus infinity equal to ERFC plus infinity equal to 0, and ERFC minus infinity is equal to 2. So by replacing this value, we have equation 2. So this is now the steady state solution. Okay, and you can see that the steady state solution also satisfies the boundary condition at infinity. When z is infinity, so e power minus infinity is 0, e power minus infinity is 0, and e power minus infinity is 0. So this is the beauty of Laplace, that even at resonant case, the solution are physical solution, and they satisfy the boundary condition. Okay, equation 20 can be written as just for the study case. When we don't take the resonant case, okay, just we take the study case for which t tends to infinity. So equation 20 will take this form. Okay, okay, okay. I didn't change this by 2 big omega, because I did it. This is the general case. Now we have all the 3 cases here. 2 omega is equal to 2 omega, omega greater than or less than. Okay, so this is the general case, but this is the study case, independent of time. So also, one scholar has asked about the question about this. This is quite interesting. The question was, and the query was quite interesting, that why you don't put t, because look at this one. If you put t tends to infinity, I didn't put in here. So this is not t. This is the phase angle theta. Omega t is actually theta. Okay, this is not t. Look at here. Here we can see in the equation 20, this is t. This is not, this is omega t. This is cos theta, cos omega t plus iota sin omega t. So this is the phase angle. Okay, so this is the angle, and this is t. So only we will replace t to infinity here, not in omega infinity, because this is one value. Omega and t is not two value. This is one value. This is the phase signal theta. So that's why we don't replace t to infinity here, because this is not t but this is omega t. Okay, so remember, clear your confusion about this point. This is quite interesting and important. So now we have, this is the study case of equation 20, and in all the cases when the force frequency is greater than, less than, or equal to, okay, the natural frequency. This is now is quite important, and this thing is new. Now we are going to, okay, the next step will be new for you, and you have to do when you have such kind of situations. And this is quite important, because in this we will find the order of the thickness of the boundary layer. Okay, the thickness of the boundary layer. So how to measure the thickness of the boundary layers? We will have that how many boundary layers are produced or developed in this flow. So actually 3 boundary layers are developed in this flow. 3 boundary layers, okay? So that 3 boundary layers are, because we have minus u a1 a1 u1 e power iota omega t, and a1 u1 b e power minus iota t. So we have 3 boundary layers. So 3 boundary layers will be produced. Okay. So we can write the above equation as like this. Okay. This equation 23 can be written in this form. This simple form is minus z alpha 1 iota beta 1, and this one the radical has been replaced by alpha 2 iota beta 2 and alpha 3 iota beta 3, where alpha 1, alpha 2, alpha 3 are the order of thickness of boundary layers. Alpha 1 is the first boundary layer, this is the first boundary layer, this is the second boundary layer, and this is the third boundary layer, because we are considering the real part, the real boundary layers, not the imaginary boundary layers. So that's why we don't care about beta. Okay, you can see here we have replaced alpha 1 plus iota b1 by this thing. Look at equation 23 or 23, I think. Look at this one. This is alpha 1 alpha plus iota beta, alpha 1 plus iota beta 1. This is alpha 2 plus iota beta 2. This is alpha 3 plus iota beta 3. So we are alpha 1 iota beta 1 is equal to this thing. Okay. So how to find alpha 1 and beta? What are alpha 1 and beta 1? Because this is the sum of these two. So what will be individually, what will be alpha 1 and what will be beta 1? Because we need alpha 1, not the sum of these two. We need alpha 1 because this is the thickness of boundary layer. This is the order of the thickness of boundary layer. So how to find this alpha 1? Let me try to find this alpha 1. Similar procedure you can adopt, okay, for the alpha 2 and alpha 3. I will just solve this one. I will calculate alpha 1, and then you can calculate alpha 2 and alpha 3 by using the same procedure. Just taking square of both sides. So we have alpha 1 square minus beta 1 square plus 2 iota alpha 1 beta 1, and the square root of this is just this thing. Okay, now compare the real and imaginary parts. Compare the real. So this is the real part, and on the right hand side the real part is only this thing. The imaginary part is 2 alpha 1 beta 1, and this is the imaginary part. So now from this we have to find the beta 1. So we have the beta 1 value, this omega alpha 1 nu. So replace this into this equation. Replace the beta 1 value here. So when you replace, now put beta 1 value in equation 27, we have alpha 1 square. Look at here, alpha 1 square minus beta 1. So minus beta 1 means omega beta 1 square omega square alpha 1 square nu square equal to W naught square by 4 nu square. Now uh, convert this into a standard form. So when we multiply alpha 1 square to the both side of equations and then rearrange, we get this one alpha 1 4 minus W1 square by 4 nu square plus alpha 1 square minus omega square nu square. So look at this equation 29. It is a biquadratic equation. It is a biquadratic equation. Okay. So first we try to find is the biquadratic equation. So let we find alpha 1 square first, which is equal to minus b plus minus b square minus 4ac 2a. So that means alpha 1 square is equal to this thing plus W naught at nu square plus minus 2 and this thing. Okay. And so alpha 1 is equal to this thing, alpha 1 square. So what will be alpha 1? Taking square root on both sides. So alpha 1 is equal to plus minus this thing under the root. Okay. Nothing else. Alpha 1 is the under root of this thing. Plus minus will be here. Okay. This will be plus minus because the square root value. Okay. So select the positive root. Now this will give you alpha 1 and beta 1. The positive root of this plus 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 will be the alpha 1 and the negative root, okay, minus, and that will become plus when we multiply this. So that will become like this. Alpha 1 select select the positive root as alpha 1 and the negative root as beta 1. Okay, from the when you take alpha 1 square, so we have plus minus here. This is plus and this is minus. So the plus root plus into this thing and minus into this thing. So plus into this thing is the alpha 1 and minus into this thing is. So now it becomes minus W naught square. So this is alpha 1 and this is beta 1. So now this is the bondelier thickness. Okay, this is alpha 1. And the bondelier thickness can be found by this formula 1 by alpha 1. Now you can find by using a similar procedure to find alpha 2. So you can do like this. Eliminate beta 2 from here and then put in this equation, and then it will also give you biquadratic. Okay, so take the then this will be your alpha 2 and this will be beta 2. Similarly, this will be alpha 3 and that will be beta 3. So this will be beta 3. Okay, this is not 2, this is beta 3. So all the three bondelier have been found. Okay, now the study solution 24 indicate the existence of three distinct bondeliers. We calculated three distinct bondeliers of the thickness of order. Look at this one. This will be the order of the thickness of order this 1 by alpha 1, 1 by alpha 2, 1 by alpha 3. This will be in the denominator alpha 1. And let me discuss that. If we have 1 by alpha 1, so look at this one. 1 by this thing, 1 by this thing. So this will be in denominator. So look at, what if we conclude our lecture? So what will be the conclusion? In the conclusion, it is clear that the steady state solution 24 and the associated bondelier decreases with an increase in suction injection parameter. You can control the bondelier by suction injection parameter W naught and remains bounded for all values of oscillations. When W equal to 0, when the oscillation is 0, then all the thickness, all the bondelier thickness will overlaps each others. The three bondeliers come together into a single layer of thickness 1 by alpha 1. If omega is equal to 0, if you if your imposed frequency is equal to 0, then you will have one boundary layer. All the three boundary layer will be combined. Okay, then there will be no separate boundary. Alpha 1 will be alpha 2 and alpha 2 will be equal to alpha 3. So look at this. This is quite interesting. That what is the effect of the suction injection parameter on the boundary layer thickness? Okay, look at this relation. Alpha 1 is in the denominator, so it means the boundary layer thickness. Okay, the boundary layer first boundary layer thickness is equal to 1 by alpha 1. So it depends on this thing. You can see here alpha 1 in equation. Look at this one, that it is in the denominator. When you increase this w naught square, because it is the reciprocal, the boundary layer thickness is equal to 1 by alpha 1. So 1 by this thing. So boundary layer thickness is inversely proportional to this equation. So when you increase w naught square, means suction injection parameter, so when there is more suction injection, the boundary layer thickness, the order of boundary layer thickness or the boundary layer thickness will be decreased. Okay, you can control the boundary layer by adjusting this suction injection parameter. While increasing this parameter, the boundary layer thickness will be decreased, because this is the inversely proportional boundary layer thickness, and this is the denominator 1 by this thing. So this is quite interesting result from this one. If you want to control the boundary layers, a boundary layer is not coming to the steady state, not coming to the equilibrium points, you can introduce the suction injection, and that will be control your boundary layer. Okay, and if you absent the force frequency, if you want to the imposed oscillation make equal to 0, then we will have only one boundary layer. All the three boundary layers will come together into a single boundary layer. Okay, now this is the equation is only for w naught. Okay, if you look at equation number 24 or equation 20, this is only for w naught greater than 0. Okay, of course, because in all equations we have w naught. In equation 20, which is the main general solution, this is your equation 20. So you can see we have calculated this per w naught. So this means the equation 20 has been solved for the suction. Now if you want to calculate this for the injection, so replace this w naught by minus w naught. When you replace w naught by minus w naught, so it will becomes w naught by 2 nu z. Minus will be become positive. The minus into minus into minus w naught, so it become w naught by 2 nu z. So you can replace where there is w naught, you can replace this by minus w naught. Okay, and that will be for the injection. So for the injection, all the equations up to equation 25, 26, sorry, the last equation, the steady state solution 24. So all these equations, these values are for suction, not for injection. Okay. So if you want to solve for injection, so please incorporate replace w naught by minus w naught. Look at this equation 23. Just change w naught by minus w naught. So if you change in the 20 equation 20, and again repeat all these equations, if zts, but there should be minus is plus w naught, there should be minus w naught square. Again it will become positive, because w minus w naught square again positive. So these will be changed. this will be positive, this will be positive, and this will be positive. Okay. So in the blowing case or injection, injection is also called blowing because it blew out. Okay. Sometime when you uh, dig the well, okay, and the waters comes out from the ground, from the deep ground, so that is called blowing, and this is called injection. In case of injection or blowing, by replacing W naught with minus W naught in equation 20, look at here, with minus W naught in equation 20, it is noted that the resonant solution, that is steady blowing, does not satisfy the boundary condition at infinity in the resonant solution. Yes, I have found already. So let's come to the resonant solution and try the condition at infinity in the equation uh, 21, I think, because 21 has been the study case for resonant for resonant. Look at this one. Okay, now this equation 2 is the study case, study resonant case for the suction. For injection, change this W naught by minus W naught. So uh, we will have plus W naught by Z. Okay, so we have when Z tends to infinity, and also in this case we will have e power plus W naught by Z naught, and also we will have plus by e power Z naught. Okay, but if you find that e power infinity, but we have e power plus infinity and also e power plus infinity, but in the bracket we have e power minus infinity and e power minus infinity, e power minus infinity. Okay, so e power plus infinity and e power minus infinity. So e power plus infinity uh, tends to infinity. So it means that at resonant case for suction, uh, this equation doesn't satisfy the condition. So how to satisfy this condition? Also, we can satisfy this condition. Now, what will happen? The bondelier for the blowing, for the injection will not be controlled. The bondelier will be, the result will be infinity. That means the bondeliers are not controlling. Both the bondeliers move towards infinity. So at infinity, when we for the injection, that is when W naught is replaced by minus W naught, so the result will be plus W naught by Z, plus W naught by Z, and when you put here Z tends to infinity, so the result will be infinity, and 22 does not satisfy the infinity condition for the injection. Okay, so this is the drawback. So for the injection, our equation is not a physical solution. Our equation 21 is not a physical solution. Okay, the steady case solution, the unsteady case is okay. Okay, let me try to look the unsteady 20, equation 20. In equation 20, yeah, because of ERFC infinity, because in this case we have ERFC infinity is 0, ERFC plus infinity plus infinity plus infinity is 0. Okay, yes, we have this 0, ERFC infinity. So 0 multiply this thing, so it becomes 0. Okay, and it moves faster than in 0 as compared to this thing. So that's why an steady case is it seem uh, physical, and it satisfy the condition. But equation 22, Yeah, this 23 equation, because it is the resonant case. No, not equation 22. Sorry, equation. Yeah, equation 21. Yeah, no, equation 21 is, and both are same. Yeah, both. So let me check 23. Yeah, equation 22 in the resonant case. So it doesn't satisfy the condition at infinity. Okay, so it means the solution for injection uh, far away from the plate is not a physical solution. So it may be replaced if we can do to control the boundary layer at infinity. If we take the magnetic field hydro image d, if we take the image d, so we can control this, and even on the steady case and the resonant case it will also satisfy the boundary conditions. Okay, so this is the end of this lecture and also the end of this semester. Okay, so and I hope that I uh, hope for the best, that best of luck, that you will face the final examination in the coming week. Okay, so we hope for the best, and try to prepare yourself for the final term examination. And those students who are in the second semester and will be shift to the research phase, is also directed that after examination, when you finish your exams, so try to write application to the your concerned supervisor. Okay, um, to whom you are want to work research work, uh, to start your research work. So try to um, write and send application to the department. Okay, to the coordinator, uh, uh, the coordinator of main coordinator of our academic portion is Amna, and the research coordinator is Anis Imtiaz. So you can submit your applications to the concerned supervisor. Okay, write the name and the supervisor, and sign the application. Okay, so then uh, I hope that after exams we will start. Okay, the next phase, research phase. So this is the end of this lecture.